All right. So today we're going to take a look at a couple questions in regards to a well-behaved utility function. These are oftentimes referred to as just Cobb-Douglas utility functions. So one important thing to note is just that we're going to refer to our two goods in this case is just x1 and x2. And the first step to solving one of these questions would usually be to graph. So I'll just show what the output might look like on a graphing calculator. This is just kind of, in general, what you would get for any sort of well-behaved function. And the whole point of the ordinary demands is to find the optimal bundle of x1 and x2 that the consumer will, consume. And, in order to start doing this, we first need to calculate for our marginal rate of substitution. The MRS is what we will refer to it as, and it simply measures the rate at which a consumer is willing to give up units of one good in exchange for one more unit of another good, while keeping the overall utility constant. In other words, it shows how many units of good Y, or x2, a consumer would trade for one additional unit of good X, or x1 in the case that we're going to work with. So in order to do this, you have to calculate like the partial derivatives for each individual good. We will do that, but one thing that I found helpful to save time on exams and things like that is just to remember this equation here. You can think of any time that there is a Cobb-Douglas, it's going to have some sort of exponent in either of the two spots where we have our constants A and B. And you can just put them on this equation here to get your marginal rate of substitution. So if we look at this case, we have 1/3 acting as our A and 2/3 acting as our B. So we would have 1/3 of x2, then we would have 2/3 of x1. And remember, this is always going to be negative for the marginal rate of substitution. And we would just end up canceling the two denominators on the numerator and the denominator, which would give us our marginal rate of substitution for this question to be 1/2 x2 x1, which just simplifies down to x2 over 2x1. Which that is convenient, but it is still helpful to remember how to do this in case you are required to show work or something. So we will do it with the partial derivatives now as well. We could also rewrite this because we have x1 to the 1/3 and then x2 to the 2/3 power for our utility function. And we could just rewrite this in natural logs to make it easier to derive. So we could rewrite this as 1/3 of natural log of good 1 plus 2/3 natural log of good 2. So for the partial derivatives, we just want to take for each individual one because the marginal rate of substitution is equivalent to, the derivative with respect to x1 over, respect to x2. So the derivative of the utility function with respect to just x1, we know that the derivative of natural log of x1 is just going to be 1 over x. So for this first one, this is going to be 1/3 of x1. And then for the second one, it's going to be just 2/3 of x2 for good 2. And when we put these together, it's gonna look weird, but we can, use some methods to simplify here. All right, so looking at this, it does look kind of ugly, but we're just going to use the ear method here to kind of distribute these terms and find our marginal rate of substitution. So for the numerator, we're going to use the bigger part of the ear, which is just the 1 times 3x2, or good 2, which is going to be 3x2 on the numerator. And then for the denominator, it's going to be 2 times 3 of good 1, which is just going to be 6 of good 1. Which this is just going to come down and simplify to 1 of good 2 over 2 of good 1. And we have to remember that this is always going to be negative. And if we compare this to our number that we found earlier, we have minus x2 over 2x1. And then here in this case, it's kind of hard to see, but we do have the same thing. All right, so now that we have our marginal rate of substitution, we can start solving for our demands. One thing that we have to do first is we need to set our marginal rate of substitution equal to our budget constraint. And in order to do this, we just take our number from earlier, which we got from doing the derivatives. And we need to set this equal to our budget constraint, which is just going to be the prices of the two goods. We also are going to make sure you remember that these are both going to be negative, but in this case, we're just going to cancel both of them out. And we want this to be all in terms of x2 because we're going to plug this into our budget equation here, and we want to be able to sort of simplify. So we're going to multiply both sides by 2x1, which is going to isolate the good 2 into this, which is going to be p1 over p2 times 2 of x1, which, if you want to make it easier to think about, is just going to be the same thing as saying 2p1x1 all over p2. And then when we plug this into our budget equation, we're just going to get m equals p1 x1 plus p2 x2. And we have our x2 here, right? So all we're going to need to do now is just plug that in for our variable. And we can do some simplifying now and get rid of our p2s. And it's going to leave us with p1x1 plus 2p1x1 equal to m, which is our budget. And we can just simplify this to m equals 3p1x1. And we want this to be in terms of x1 in order to find our ordinary demand, as talked about earlier. So we just divide by 3p1 on both sides, and we're going to find our first ordinary demand is going to be equal to m over 3p1. So that will be good to know for later. Now we're going to solve for our second ordinary demand. And earlier we did write out that, remember, we had like our x2 is equal to our 2p1 x1 all over p2. So we actually ended up solving for, our x1 now. So we're just going to plug that in to find our x2 without having to, do the whole budget equation again. So our x2, I also find it kind of helpful to space out our variables here to not get confused. One thing is we can, the bottom denominator here is the same thing as having a 1 here. So if we were going to space this out, we could write like 2 over 1 times p1 all over p2. And then multiply this by our x1, which is our ordinary demand that we just found, which is being our m over 3p1. If we do all this, we can see like our p1s are going to cancel out. And it's going to just leave us with our ordinary demand being 2m all over 1 times p2 times 3, which is going to be 3p2. And just like that, we've calculated the ordinary demands of this utility function. So with this, there are a lot of other things that we could be asked to do, like, for example, graphing the inverse demands. In this case, it just wants us to do it for good 1. So we're going to pull back up our workspace from earlier. Move it down here. So our demand for good 1 here is m over 3p1. When it says for the inverse demand, that means that we're just plotting it with p1 being on the y-axis and in terms of good 1. So in order to do this, we are going to just start by kind of backtracking a little bit, setting, our ordinary demand, right? But we want this to be in different terms, so we can change this to 3p1 x1 equals, m. And in this case, we'll just actually divide by 3x1, so that way we have p alone, so that way we can see, what it's doing, kind of like as an isolated term. So our x1 equals, our p1 in this case equals m all over 3x1. Now, if we wanted to graph this, because this is going to be our function, right? We are going to just look at, what different values of x1 are going to be, because this is our x-axis. So let's say we're plugging in like 0, 1, and 2 for all these. If we plug in these values, let's say I have our 1 and our 2 here. If we plug in 0 here, it's going to make our function undefined, and we can't do anything with that because it would be like dividing by 0. Whereas if we plug in a 1, it's going to just be the same thing as saying m over 3 times 1, which is just m over 3. And then if we plug in a 2, it would just be m over 6 because we're multiplying it by 2. And our demands would look, or our inverse demands would just look something of this sort, where there would be like an asymptote down here and it would never touch because it would always just get infinitely closer to 0. But it would never touch. So that's kind of all it's asking there. We're going to kind of be looking at a similar concept here for the, the Engel Curves, a good one. Engel Curves, a good one, however you want to pronounce it. So we're going to use our demand from earlier. We have x1 equals m over 3p1. Now, in this case, we actually want to leave our m is the isolated variable on the y-axis and still leave it in terms of good 1. So this is going to be very simple. All we're going to do is we're just going to multiply by 3p1, and we're going to be left with m equals 3p1x1. In this case, if you plug in 0, this whole is just going to be m equals 0, right? Whereas if you plugged in 1 for 1, if you plug in 1 for x of 1, then it's just going to leave our m equal to 3p1. If we plug in a 2, our m is just going to be equal to 6p1. And it's going to leave us with a linear line for the graph, just with a slope of 3p1. Because for every 1 unit of x it moves, it's going to go up, 3p1. So anyways, that's all I got for today. Thank you.